I'd like to show you how to use Excel to solve a very traditional air compressor power analysis problem, starting from the air tables that I've made available to you in Excel on Jay's Toolbox. So let's go ahead and get started. This example problem is going to require that you pretty well have been through chapter 6, especially as it relates to reversible and adiabatic processes. And so in this video, what I want to do is demonstrate from scratch a step-by-step problem-solving technique within Excel. Now, we're going to start with the basic problem-solving approach, whether you're using Excel or pencil and paper or MATLAB or Mathematica or any kind of problem-solving platform. And then I'm hoping that I'm going to be able to pull off, starting from scratch, using the Excel Airtables, and then go through step by step to solve the air compressor problem in Excel. So here's our problem. I need to use an air compressor for a steady state, steady flow of 11.3 cubic meters per minute of air. That's volumetric flow rate. Starting at 100 kPa and 25 degrees C, that's a lot like standard atmospheric conditions, and compressing up to 793 kPa, or about 8 atmospheres. And the question is, what is the minimum power needed to run the compressor? This is a very common mechanical engineering question that we engineers are asked all the time. So let's plan the solution before we get into Excel. And so let's see, we always start with a sketch. I thought I'd throw in an image of here's what an air compressor looks like. Now it's all closed in a box, so it looks very simple. Ingersoll Rand air compressor on a trailer. But here's our sketch of a very traditional steady state, steady flow compressor. Inlet state 1, outlet state 2. We're compressing the air. That's why we have that trapezoid that's decreasing in size. In other words, the specific volume is decreasing, pressure is increasing. I haven't showed heat transfer on my sketch because we're going to say that this compressor is fully insulated, but I am showing W dot out from the open system is less than 0. I better there we go, drag my picture down here. W dot out is less than 0. In other words, power is required to drive the compressor. So let's just write down things we know about this problem statement. Our substance is air, and we're going to model our air as an ideal gas, and this time with variable specific heat, because we're going to expect the temperature change to be significant. We're going to use the air tables. We've got an open system, steady state, steady flow, 1 inlet, 1 outlet. The air compressor is going to be fully insulated, so the heat transfer rate is 0. And then we think about, this isn't given, is it? We have to think through the second law, and we think, well, what would be the least amount of power needed to drive this compressor? The least amount. Well, that would be the situation where the compressor is reversible and adiabatic. Not just adiabatic, but reversible. Because doesn't it make sense that if there was some type of irreversibilities within that compressor, like some lost compression of the air or some friction within bearings within the housing, that would require more power than the reversible and adiabatic situation. So we're going to study the reversible adiabatic situation, and that would correspond to the minimum possible power needed to drive our compressor. Okay, let's continue on with the sketch with a temperature entropy diagram. We're starting at P1 at state 1, okay? Let's see, reversible adiabatic. That's a vertical line, isn't it? Constant entropy up to P2 and state 2. Vertical line, so S2 equals S1. Okay, and then here's our sketch again. Let's see, what else do we know? Determine the mass flow. That's how we have to think through how will we solve this problem. we're not given the mass flow. We've got to figure it out, don't we? So we do have enough information to determine the inlet specific volume using the ideal gas relationship. And then we're given the volumetric flow rate, AV, at state 1. So that's how we'll get the mass flow rate. Let's see, we will write, since we know T1, we can write down H1 and PR1. And we think ahead in chapter 6, for an isentropic process, the ratio P2 divided by P1 equals PR2 over PR1. So that's covered in your chapter 6. That's not just a formula. It's covered in chapter 6 for the air tables. Okay, that's very important. And so let's see, we have enough information here now to determine PR2. Well, if we have PR2, we can go to our air tables and we'll look down the PR column and kind of back calculate H2. And as a courtesy, we'll determine T2 as well, since we know we can solve for PR2. Now, once we've got H2, okay, I'm pretty good at the first law of thermodynamics, the energy balance. And so the first law says Q dot in, that's 0, adiabatic, minus W dot out, what we're looking for, equals M dot times H2 minus H1. Lo and behold, I've found M dot, I found H2 and H1. And so lo and behold, W dot out, isentropic, I hope it's going to be a negative number, is equal to M dot times H1 minus H2. And so that's our solution approach. And notice here that all this written down stuff doesn't have anything to do with Excel. So you would write this sort of stuff down somehow, whether you're working in Excel or on pencil and paper or in MATLAB or Mathematica or whatever problem-solving platform you're using. Now let's plan our work in Excel. We're going to open up the basic. Now, I did a copy and paste, and I see it jumped right out at me now after proofreading 15 times here, the 16th time around. Open up the basic air tables tool, not steam tables tool, and then we're going to save as with a good file name and a good location. Okay, open up the air tables tool. We will delete the unneeded tabs. So our input data is SI, so we're going to delete the English units tabs. And we're going to try to remember to save frequently. We're going to need to create and name 2 additional tabs from scratch. And we'll call one demo problem. That's where we're going to write down the given information and the problem statement, sketches. And then we're going to have a second tab that is the numerical solution. We'll flesh out the intro tab with sketches and the solution plan. I hope that I've got things prepared for that rather than having to put them in from scratch. And then we're going to work through the solution tab. We're going to work down the sheet. We're going to explain the work and include the units. That's going to be important for all problem-solving platforms. Okay, so this is my signal to go live. Let's see, so I've got to get out of PowerPoint. I made it. At least I'm out of PowerPoint. Let's go to the browser. Here I am at J's Toolbox, jstoolbox.vt.domains. Let's drop down the Toolbox menu to Excel Docs, and then we're going to go down to Air Systems, Excel Air Systems. Okay, so we're on a new page now. We're going to scroll down, and here it is, Thermodynamic Properties of Air. We're going to click the download button. Now, I already had this on my PC. You would click the download button to possess this Excel file saved to your PC. All right, so let's go to Excel. And then I'm going to load in. I'm going to start with my source document, Moran Air Props Lookup. All right, let's plan ahead. What's the first thing we do? Oh, I think the first thing we do is we save as, because I don't want to ruin my source document. File, save as, and let's see. I'm in the right folder. Let's call it air compressor demo. Air compressor demo. Okay, so sure enough, now let's check our work. Yep, I've got a new file name, air compressor demo. My source document is saved, safe and sound. Now let's start destroying tabs we don't need. Lookups English, don't need it because we're in SI. You could say that you don't have to delete these, but for simplicity and for future work, it's kind of a good idea to stay as simple as possible. All right, so now we're going to create two new tabs. I'm going to go to this Create Workbook Worksheet tab, okay? Sheet 1, terrible name. So let's see, right click, rename it, and I'm going to call it Demo Problem. And I'm going to move it, drag it to the left. I'm going to create another worksheet, sheet 2, like terrible name, rename. Let's call this Solution. And drag it to the left, okay? And so now I've got, and let's see, I've got size 10. I like that font size. Demo Problem, that's good. Font size 10, all that looks good. And so let's see, a title of our file, not the file name. Demo for air compressor power. I'll make that big, make it size 12. It's generally good practice to say what the file name is. Air compressor demo.xlsx. You'll see that I don't leave spaces in between my file names. By me, on, and today is 6/3/2024. Okay. We would start typing in problem statement, but it's my hope that I've got it. I hope I've got a screenshot of it so I don't have to type it in. Insert a picture, and we're going to go to live demo, and let's see. It is, I'm looking for an image, zero problem. I've got air demo problem. Here we go. There it is. Sorry about that. So there's our problem statement. Let's see, what's the next thing we did? We started with a sketch. We could create a sketch in Excel, but just to save time, let me see if I can find my sketch. Here it is. Now, I've got this stored in my library of sketches, so that's pretty automatic for me. Now, the TS diagram, we could draw it in Excel, but again, to save time, I think I've got it. So you can see here on this little thing, I'm going to right click and format picture. I'm going to draw a box around the image, turn it black, make it a little thicker. So you can see that I created this image in Excel over in a different file, and I just made a little screenshot of that to save time. Okay, so there's our sketch, our TS diagram. We would describe how will we solve the problem before we get into the hard work of solving the problem. And here, it looks like here it is. This is just a screenshot of the PowerPoint slide that I was showing you. So I'm in pretty good shape there. Okay. So I think that's good. But do you see that we've documented on one tab sort of what we're doing before we start doing it? Okay. So here's our solution. Now, I like to copy and paste my problem statement on my solution to keep myself straight. So here's my solution. Maybe I'll title this solution. You don't have to, but kind of a nice, okay. So let me, okay, so I have to remind myself, let's see, what did we say we were going to do first? The first thing we're going to do is use ideal gas equation of state to determine little v. Ideal gas equation of state to find V1. Okay, and so let me turn that bold, okay? And what do we need? We need R for air, 0.287. Now, I've got that by heart because I used this R value for air both in undergraduate, graduate school, and then working for a living. So R for air in kilojoules per kilogram degree K. So I know what R for air is, okay? Let's see, pressure in kPa, pressure 100, P1 kPa. Need to turn that, yeah, I just fat fingered in the number 100, okay? T1, T1 in degrees C, okay, that's 25, okay? Now, looking ahead, of course, you know I'm going to need absolute pressure, absolute temperature, right? T1 in degrees K. Well, let's see. I'm going to add, it's a formula, a simple formula equals whatever that number is plus 273. So there's T1, okay? And so V1 in meters cubed per kilogram is, let's see, is RT1 over P1. So I'm typing that out in text to remind myself what I'm doing. Okay, equals, now it makes it easy, R times T1, absolute temperature, divided by P1 in kPa, makes the units come out right. And so there is V1. And so that's a nice little piece of work. So let's just go ahead and box that out. Okay, the volumetric flow rate, 11.3. That's going to be AV1. And the units are meters cubed per minute. Okay, I just fat fingered that in. Okay, V1, meters cubed per kilogram. That equals whatever that number is. And I'm going to turn that blue. So if you've watched enough of my videos, you're seeing that I color very simple formulas where I transfer a number from one place to another in Excel. I just turn that blue, okay? And so M dot in kilograms per minute equals AV1 over V1. I think that, yes, that's correct, isn't it? Okay. So equals cubic meters per minute divided by cubic meters per kilogram. So that's going to be kilograms per minute, isn't it? All right. Now let's look ahead. When we go to the first law, typically we like M dot in kilograms per second to get our unit straight. So let's go ahead and calculate it right now. Kilograms per second. Well, do I need to explain that? No, not really. That's so straightforward. It's whatever that number is, kilograms per minute, divided by 60. 60 seconds in a minute. So yeah, kilograms per second is a small number compared to kilograms per minute. All right. So let's see. Let's box that out. Pretty good piece of work. Okay. Let me see. I'm going to look at my cheat sheet. And the next thing we do, let's see, the next thing we do is we need to get, our process is reversible and adiabatic. Okay. We need to get H1 because we're going to go to the first law. Also, we need PR1 because we've got a reversible adiabatic process and we've got to figure out what T2 is. So let's see, we need we find PR1. How will we do that? Need to find PR1. Let's go to our lookup SI and let's look at this block up here where we enter it. We know T1, don't we? And we can get PR if we know the temperature. So let us grab this block of cells, copy. So I've got this whole block of cells in the clipboard. So copy, okay. Solution, I've got to go to the A column. That's the only restriction, but I'm going to paste it in here. Now our temperature is not 290, is it? Okay. It's, what is T1? It's 298. So I'm going to make that simple connection, simple equation equals T1. Boom. And I'm going to color this blue because I just transferred that in. Okay. Let's need to find PR1 since T1 is known. All right. Wow. Okay. Well, there it is. There's PR1. It's just found. And so let's just make a simple formula instead of instead of getting confused, let's work down the page. So there is PR1. Okay. And how about H1? Kilojoules per kilogram, because we're going to need that. There it is, 298.18. Look how easy that was compared to interpolating by hand. Okay, so we've got PR1. Okay, so the next thing, what's the next thing we need to do? Find P2 using isentropic relation. Okay, so I'm going to make that bold because that's what we're doing here. Okay, what do we need? We need P1. And so instead, let's just say what it is. There's P1, okay, PA from above. How about P2? We haven't entered P2 yet, have we? So we'd better enter it. It's 793. 793. All right, let me get my colors straightened out. I'm going to box it. I'm going to turn that blue since I just brought it down with a simple formula. And 793, I just manually entered that. And how about PR1 from above? Just to keep ourselves straight. You don't have to do this, but it's just sort of a courtesy. Well, I need to box out both of those. And I'm going to turn this blue. And so now I know let's see, PR2. PR2, I can solve for PR2 equals PR1 times P2 over P1. So I type that out in text. And now my formula becomes very easy because in front of my eyes, I see what I need to do. Equals PR1 times P2 over P1. And it looks like I did something wrong. So let's check my formula. Equals A36, PR1 times A35, yep, divided by A34. I must have put in a stray parentheses or something like that. So there's PR2. Let's box this out. What's the next thing? We have PR2 now. We need to determine H2, and as a courtesy, T2. Find H2 and T2 now that we know PR2. I'll put that bold. So I'm kind of explaining what I'm doing. All right. How will we do that? Let's go back to our lookups. So we have PR2. Wow, look at this block right here. Used for known PR. So let's just grab all of this whole block, copy. We've got it in the clipboard. We'll go back to our solution. We've got to go to the A column and paste. Okay. Well, PR is not 1.2. It's whatever this number is. So I've got to, instead of manually enter it, I'm going to transfer my number down. Equals whatever PR2 is. And I better turn it blue to keep myself straight. So I'm not fat fingering in a number twice. All right. Well, look at this. Here's H and here's T. Okay. So here it is. So H2 in kilojoules per kilogram. We'll just keep, so we're working down the page. Let's just click on that cell. And for T2 in degrees K. Okay, nice block of work there. And so finally, okay, we have H2, we have H1, we have M dot. Use first law, steady state, steady flow, one inlet, one outlet, adiabatic. Find W dot. Okay. And so let's get our numbers together. Let's get M dot in here. There it is. M dot in kilograms per second. Instead of starting with the formula, let's organize our work and say what we're doing. Oops. I need to box in. So there's our number, M dot. Probably a few too many significant figures, but we can straighten that out later. M dot. How about H1? It's from above. And let's see. Let's fish it out. There it is. How about H2? So again, you're going to say, well, why is he doing all this repetition? Well, I do this repetition not for demo purposes. I do this as part of my work so that when I come back and use this very much of a template type problem next year, I can very easily see what I was doing a year ago. Okay. And so W dot out in let's see, units, that's going to be in kilowatts. That's going to be equal to M dot times H1 minus H2. I'm just typing this out in text. So remember, some of you might say, well, why'd you get H1 minus H2? It's because I'm getting the minus sign out on the left-hand side of the equation of W dot. And so that's equal to M dot times the quantity H1 minus H2. I hope I get a negative. Yes, a negative number. W dot out is a negative number. Yes. And so let's say power minimum power needed to drive the compressor in kilowatts equals the negative of this. And probably makes sense to get our number, at least for the final answer. Let's make our number, I think, probably 2 decimal places to the right. Okay. And then we'll box out our solution here. Let me check over here. Yep, I think I'm looking pretty good. I'd already solved the problem, and I just want to check to be sure I didn't make any careless errors as I was blabbering and working at the same time. But let's reprise what we did. Okay, there's our solution, just like that. I didn't time myself. We'll have to figure out how long it took. But problem statement, I used the ideal gas equation of state-defined V1. I calculated the mass flow rate since the volumetric flow rate was known, just got V1. This is the beauty of planning ahead. Okay. Now, let's see. I knew T1, so I know I've got to analyze the isentropic process for the minimum power. So I found PR1 using this interpolation block with the air tables. I solved for P2 using that isentropic relationship. PR2 over PR1 equals P2 over P1. Found PR2. Then I used another interpolating block in the air tables in Excel with PR known. There's that nice blue cell to show that I transferred it into my interpolation block. And so there H and T appeared. Now that I've got enthalpy H, then I've got everything I need for the first law, apply the first law to get the minimum power needed, 53 kilowatts. And there it is. Oh, file save, right? So I did all that work. I don't think I saved it once. And so I do that a lot, forget to save my work, and it's very frustrating. So there it is. Let's see, let's go back to PowerPoint to recap. Okay, what kind of things did we do? We destroyed the unneeded tabs. We started out with the Moran air props lookup table. Okay. We clearly documented the problem being solved in one tab. We started with a sketch and we outlined the solution in text and sketches. Okay. Demo problem tab. Then we went into another tab called the solution tab. Okay. And there's what we did. We copied and pasted 2 lookup blocks into the solution. We explained our work throughout. We included units. unit stated throughout. We worked down the sheet, explained the work in text. Okay, I plopped down. This is when I solved it the first time offline. I made a little screenshot of the first law, and we clearly showed what we wrote out. What is the answer to the problem asked? Minimum power required 53.08 kilowatts. Okay, what are the takeaways from this video? Save as was critical. We started with the basic, and there's my blunder again, Excel Steam Tables tool. We started with the Excel Airtables tool. That's the downfall of copy and paste, isn't it? We created and named the plan tabs. We started with a sketch, even in Excel, okay? And then we implemented the solution. We worked down the sheet, explained the work, and we included units. Okay, so except for that blunder of Steam Tables, stealing slides from my Steam Tables intro, I think it worked out pretty good from scratch. So I hope that helped. That from scratch a demonstration shows you that you can do this too. You can start with basically a blank Excel sheet, and you can make a darn nice engineering problem-solving presentation using Excel. If you put your mind to it, plan ahead a little bit, and make it as good looking or better looking even than a pencil and paper solution. Hope that helps, and hope to see you again sometime soon.